Today's video is on ionic bonding. In this video we will look at ionic compounds and their general nature as well as their nomenclature. So ionic bonding as opposed to covalent bonding that we've spent some time on. Ionic compounds are typically composed of metal and non-metal. So we would have elements from the left side of the table combined with elements on the right side of the table. They usually form from a metal with a low ionization energy and a non-metal with a high electron affinity. Now, this is important because low ionization energies mean weak attraction to electrons, whereas high electron affinity means strong attraction to electrons. We can also say that there is a wide difference in electronegativity. In fact, electronegativity, the difference in electronegativity is going to be greater than 1.7. So each of these cases means that we have a widely varying difference in attraction for electrons, and the end result is that electrons are going to transfer from the metal to the non-metal. So ionic compounds and at room temperature are all crystalline solids, meaning that none of them are liquids. They all take the form of crystals. Within a crystal, we can say that there is a simplest number of ions of each type in an ionic crystal that's necessary to form the three-dimensional shape of the crystal. Stop here. For an ionic compound, we have a unit known as a formula unit, which is the simplest ratio of the ions in a crystal of an ionic compound, such as in NaCl, plain table salt. We would have one sodium for every one chloride within the salt crystal. But if we had calcium chloride, CaCl2, we would have one calcium for every two chloride within the salt crystal. These formulas do not represent independent objects the way, for instance, water would represent an independent object. We should be able to have one molecule of water existing independently, but the ratio does not represent something that we know to exist. It just represents the ratio between the ions, but we can handle it the same way. So let's take a look at using Lewis structures to look at bond formation between ionic compounds. If we were to look at sodium, sodium has one electron dot because it's in group 1, one valence electron, and chlorine, 1, 2, 3, 4, 5, 6, 7 electron dots. During bond formation, the one electron that's here is going to transfer to chlorine. That's going to give sodium. In fact, if we were to write the electron configuration for this, this would be, sodium would be neon 3s1. So our 3s1 electron is the one that's lost here, and when sodium loses that electron, it develops a positive charge, and it has the electron configuration of neon. Chlorine, on the other hand, picks up an extra electron. That would be neutral chlorine. Here's chlorine with the extra electron. This is going to have a negative charge. Chlorine originally had neon 3s2, 3p5. I don't know why I'm wanting to put brackets there. We gain one electron. That makes this neon 3s2, 3p6, which is the same thing as argon. So we would have our sodium ion. Sodium's positive, chloride's negative. The attraction is actually the attraction between the positive and negative ions. So that is the ionic bond, is the attraction between those ions. We can also use this to predict that every one sodium can supply enough electrons to complete the octet of chlorine. So we end up with the formula, need one sodium for every one chlorine, that would be NaCl. Now let's look at magnesium and oxygen. Do a little erasing here. So magnesium is a group 2 element. So we would have Mg, 2 dots. Oxygen is a group 16 element. It's going to have 6 dots. So the end result is that we would have oxygen being the smaller atom, the more electronegative, is going to gain electrons away from magnesium. And it's going to remove 2 electrons from magnesium. That gives Mg the 2 plus, and oxygen the 2 minus charge. The magnesium develops the electron configuration of neon, and the oxygen also develops the electron configuration of neon. So both of them achieve a stable noble gas configuration, but we can also see that one magnesium supplies the electrons for one oxygen. So again, we have the ratio of Mg1:1. Okay, the last one we're going to show is going to look at calcium, a group 2 element with a group 15 element, nitrogen. Alright, so we have calcium and we have nitrogen. Calcium is in group 2, nitrogen is in group 15, 5 electrons. So we transfer some electrons from calcium, the metal, to the non-metal. Okay. That gives a calcium 2 plus ion, but nitrogen is still missing 1 electron, so we have to bring in another calcium, because this nitrogen atom only has 2, 4, 6, 7 electrons. So we transfer 1 more electron to nitrogen, and that's going to give a nitrogen with a 3 minus because it picked up 3 electrons. But we have a calcium here that has an extra electron that it needs to get rid of. So we bring in another nitrogen. We transfer 1 electron, but we're missing 2, so we bring in 1 more calcium. And we transfer electrons. So we end up with 3 calciums and 2 nitrogens. And each of these is an ion also. So what we end up with is a total positive charge of +6, total negative charge -6, and +6 and -6, add those two together, that equals 0. And you can see that we have 3 calcium to every 2 nitrogen. Ca3N2 would be the final formula. In each of these situations, the energy change that occurs during bond formation is both ions develop a noble gas like electron configuration, therefore stable, low energy. So energy is given off, or these are exothermic processes, when ionic compounds form. Exothermic meaning giving off heat. So let's look at some terminology around ionic bonds. First of all, when we look at this diagram, this is a diagram showing a 3-dimensional arrangement of ions in a crystal. At each intersection of the lines, we would have an ion present. Each of these ions is a certain distance apart, and each positive is surrounded by negatives, and each negative is surrounded by positives in 3 dimensions. So some terms we have here: the lattice energy. Lattice energy is energy released during bond formation. It's also the energy required to break the bond. They're the same amount, because the energy that's released during bond formation would be the equivalent to the amount of energy that has to be put back in to separate the ions. That's law of conservation of energy. How much energy is released depends on the size of the ions. Small ions can get very close together. They're going to have very strong attractions. So smaller ions tend to have more negative values, more exothermic values for their lattice energies. And strength can also be used to compare, or we can compare their strength using things like melting points. The higher the melting point, high MP equals high lattice energy. The lattice distance is how close the atoms actually are when, how close the ions are when they're actually in the crystal. Each point, as I said, in the lattice, where we get an intersection of lines that we have here, that's known as the lattice point. At the lattice point is an ion, either positive or negative. The formula unit will be the simplest ratio of ions represented in an ionic compound. So if we look at this blue object down here, this entire thing, this whole thing, is a crystal. But the crystal is, this entire object is a crystal. Down here in blue is something that we would call the unit cell, which is just the smallest number of ions necessary to make the 3-dimensional shape that is the entire crystal. But the formula unit we described back on an earlier page is just the simplest ratio of ions represented in the compound. So let's look at ionic versus covalent properties. Ionic compounds tend to have very high melting points. Very high melting points means strong bonds. We tend to have low rates of vaporization at room temperature, so ionic compounds like salt don't convert into vapor or gas very easily. Again, strong bonds. They tend to be brittle and demonstrate something known as cleavage. Now, I'm going to go to a YouTube video and show you this property of ionic compounds known as cleavage. So this is a crystal of something known as calcite. and the person in the video is going to hit the calcite with a hammer. Notice the pattern of breaks as the hammer hits the crystal. Okay, so you can see that we get very clean breaks here, and these clean breaks along very specific lines. You can even see over here that the small shards are actually very similar in shape, still sort of some sort of rectangular solid. When we break off of the crystal, that is cleavage. Okay, again, we can see very clearly here. There's a nice smooth face here, here, and here. The crystal that's broken off over here is again a very clean cut. That is the cleavage pattern. You can see very clearly here, this is almost like a sheet of calcite. So what causes this this cleavage pattern? What it comes down to is this. We have in our crystal, we have positive, negative, positive, negative, positive. We have rows of ions. And this is, of course, occurring in 3 dimensions. I'm only showing 2 dimensions here. Well, let's suppose that we have a hammer that strikes, applies a force right here. That causes this row of ions and everything attached to it to begin sliding past this row. As this row slides down, this negative is going to encounter this negative. This positive is going to encounter this positive, and negative encounters negative. The end result is that we get a clean break between these 2 sheets of ions within the crystal, causing a clean break. That is the cleavage pattern. This can actually be used and is used by geologists to determine whether or not a compound or what we would think of as a rock is a mineral or not. Minerals tend to be ionic compounds and will actually shear under the force, an outside force, and break along clean lines. Okay, next property. Ionic compounds tend to be insulators in solid and in solid state. And the reason for that is that there are no mobile particles. To be insulators of either heat or electricity, you've got to have particles that can move, to conduct. There is no conducting particle present on these particular compounds. They do tend to be conductors in the liquid state, because once they're in the liquid state, the particles move, or they become mobile. Ionic compounds are electrolytes. Electrolytes, I don't have a good space to define this here. An electrolyte is a substance which, when dissolved in water, produces a solution that conducts electricity. This is due to dissolving makes the ions mobile. it requires two things here. First of all, it requires the movement of the particles, and it also requires that the particles have charge. And to be able to conduct electricity, ions are mobile. So electrolytes are strong. These are strong electrolytes, meaning that everything that dissolves breaks down into ions in the solution. Every ionic compound is soluble in water to some degree. How much varies widely, but all ionic compounds will dissolve to some degree because the water molecules are attracted to the charged ions within the crystals. Right, let's look at covalent compounds. Erase a little bit up here so I don't run into my... It's not going to. So covalent compounds compared to ionic tend to have relatively low melting points. This means weaker bonds. And bond is probably a bad word there. Weaker forces between particles, which I'll define later. Some of these vaporize significantly depending on molecular mass. A good example of that is H2O evaporates. If you heat up something with fat on it, which is covalent, is going to have a tendency to vaporize. That's the reason you can smell food cooking. The main thing that you smell first is going to be vaporized fats. They tend to be soft, somewhat waxy solids rather than brittle solids. If they are solids, they're crystals. The rows or sheets of particles in the crystal have the ability to move by one another without being repelled because they're not charged. They tend to be insulators in the solid and the liquid state, meaning that there are no charges. And this is primarily electrical when we're talking about the charge part. Most of them are non-electrolytes, which means, again, no charge, but there are a few exceptions to that. The exceptions include acids. All acids tend to be either strong or weak electrolytes. What that means specifically we'll define later. Their solubility depends on their polarity and also on their molecular mass. And this LDF stands for London Dispersion Force, and we will eventually define what that means. But just put that their solubility is variable. Now we're going to look at the nomenclature, how to name ionic compounds as well as write their chemical formulas. We're going to start with binary ionic compounds, where the cation, the positive, has only one possible charge. To name these, write the name of the cation, which is just simply the name of the metal, and then write the name of the anion afterwards. The anion is always going to be modified to have an ending of IDE. So anions, very important. Anions are named by modifying the end of the element name with the suffix IDE, such as chloride, oxide, bromide, and sulfide. You saw a similar process with covalent compounds. Examples would include, this is BaCl2. We name the cation. The first element is the positive, the second is the negative, so cation is barium. and chlorine becomes chloride. Notice that we are not representing the 2. There are no Greek prefixes. When we go in the opposite direction and write formulas for the names, we have to use oxidation numbers to decide on the ratios, not Greek prefixes. CaS is calcium sulfide. And then we have ZNI2 is zinc iodide. In writing formulas, you have to find the ratio of ions or moles of ions that give electrical neutrality. Everything has to add to 0 is all that means. So sum of charges is equal to 0. So examples would be strontium nitride. Okay, so Sr and N. Those are the elements that are present. Strontium is a group 2 element. That's going to be a positive 2 oxidation number. Nitride is the negative form of nitrogen, which is a negative 3. So like we have done before with acids, we bring the number but not the sign to the opposite element as a subscript. This becomes Sr3N2. We have 2 times positive 3 is positive 6. 2 times negative 3 is negative 6. Positive 6 plus negative 6 equals 0. So Sr3N2. Beryllium fluoride. Beryllium, group 2. Fluoride is the negative form of fluorine, which is negative 1. Negative 1. 2. 1. We don't represent 1s in the final formula, so we would have Be1F2. We have lithium oxide. Lithium oxide is the negative form of oxygen. Oxide is negative 2. Lithium is a group 1, positive 1. Our 2 comes to lithium. Our 1 goes to oxygen to make Li2O. Next we go to binary ionic compounds where the cation has multiple possible charges. This often involves a cation from the transition metals, or D block. And because we can have multiple charges for the same cation, we can have multiple compounds between the same 2 elements. Therefore, we have to indicate the charge of the cation and the name of the compound. Different charges give rise to different compounds. So the process is to name the cation, followed by a Roman numeral in parentheses that represents the charge of that cation, and then you add the name of the anion. Anions only have 1 possible charge, for the most part. So how do you know when there's more than 1 possible charge? Transition metals. It's a big hint. F block metals, or intertransition metals, and also lower P block. Group 1 and Group 2 always have just 1 possible charge, so they never fit into this category. So some examples would be FeCl3. In this case, we've got iron, and we've got chlorine. We've got 3 of those. We know that this is going to be named iron, Roman numeral, chloride. What we have to know is the Roman numeral. So the Roman numeral is the oxidation state. So we're going to have to find the oxidation state or oxidation number of iron, where chloride is the negative form of chlorine, which is -1. So we've got 1x, 3 negative 1s, minus 3, total positive plus total negative equals 0. Solve for x, x equals 3. We then put our 3 in the form of a Roman numeral into the name of the compound. So this is iron 3 chloride. And it actually works out that the name of Fe3 plus is iron 3. So in other words, we have to determine the charge of the cation. FeCl2, same process. In this case, we have 1x, 2 negative 1s, that adds to 0, x equals 2. So this is iron 2 chloride. CuO. Copper is a transition metal. We need to know its charge. We know oxide is a -2. So we've got x, 1x. We have 1 negative 2, minus 2, adds to 0. X equals 2. So this is copper 2 oxide. MnO2. Manganese is our transition metal, X. -2 for oxygen. We have 1X. We have 2 negative 2s. 2 negative 2s. So that's a -4 equals 0. X equals 4. So this is manganese 4 oxide. By the way, the parentheses are included as part of the name. They need to be there. Right now, this type of compound, writing the formulas from the names. These are actually maybe a little easier than the ones we did earlier. So, same as type 1, we want to combine the ions so that the total charge equals 0 for the compound. So we've got lead 2 oxide. So if we come over here, we've got lead 2, Pb plus 2. That's what lead 2 means. And then we've got oxide, -2. So we bring our 2's down. That gives Pb2O2, but this is an ionic compound, so we reduce our subscripts by dividing each of them by 2 to give a 1-to-1 relationship, PbO. Nickel 2 phosphide. Nickel 2 is Ni with a +2 oxidation state. Phosphide is the negative form of phosphorus, which is -3. So this is going to become Ni3P2. 3 and the 2 can't be reduced, so that's the final formula, Ni3P2. And then we have chromium 3 oxide, chromium with a +3, oxide with a -2. 3 goes to oxygen, 2 to give a common multiple here to the chromium. So this becomes Cr2O3. Now, ternary ionic compounds contain a polyatomic ion. So you need your polyatomic ion sheets during this. We already know what a polyatomic ion is, but just as a refresher, it's an ion that's made up of multiple atoms bonded together and they possess a charge. Has to be that to be an ion. Have to know your polyatomic ions, or at least where to find them. To name that, you name the cation. That could be either an individual element, which is a monatomic ion, or it could be a polyatomic ion, like ammonium, for instance. And then we add the name of the anion. The monatomic anion, so that would be the negative, is modified to IDE. Whereas if it's a polyatomic ion, you're going to write the name of the polyatomic ion, no modification. It's actually already been modified. So your examples include BaSO4. Barium, first of all, is not a transition metal. It's got a positive 2 charge. SO4 is sulfate, so this is barium sulfate. No Roman numeral because barium has only one possible charge. Calcium phosphate. Ca is calcium. PO4 is phosphate. In this case, NH4 positive is ammonium. ASO4 is arsenate. So 2 polyatomic ions in this case. We would just simply name this ammonium arsenate. So going in the opposite direction, the formula from the name for these compounds, you treat the polyatomic ion as a single unit. Everything still has to sum up to 0. Don't consider the atoms in the polyatomic ion separately. Consider them as one unit. So how do you recognize a polyatomic ion in a name? Well, ITE, ATE, those are 2 common endings of polyatomic ions. They're not all that way. We have things like ammonium, we have things like hydroxide and cyanide, but we definitely have these 2 suffixes showing up frequently, and they tend to be part of the polyatomic ion name. So some examples. We've got barium acetate. Okay, we can see that we've got ATE here. Barium is Ba with a +2. Acetate is C2H3O2, -1. Important to note that what's inside the parentheses here is the -1. The entire unit has that charge. So our 2 has to apply to the entire unit. Our 1 is going to go over here to barium. So our final formula, Ba, open parentheses, C2H3O2, 2. Ammonium fluoride. Ammonium is NH4 plus. Fluoride is F with a -1. We've got a +1 and a -1. That's a 1-to-1 ratio, NH4F. Aluminum sulfate. Aluminum is Al, 3 plus. Sulfate is SO4, and SO4 has a 2- overall. We have to have 3 sulfates to cancel 2 aluminum. So that gives Al2, open parentheses, SO4, 3. And then our next one, sodium hydroxide, Na positive, hydroxide, OH, whole thing is negative. So we would have positive 1, negative 1, gives NaOH. 1-to-1 ratio, no parentheses needed in that one. And our last one, cobalt 2 cyanide. We've got cobalt, cyanide, power 2. We need 2 cyanides to offset 1 cobalt. So that's going to be COCN2. Making sure that the 2 goes outside of a set of parentheses, applying to both the carbon and the nitrogen. Also be careful with cobalt. There needs to be an obvious difference in size between the C and the O. Capital C, capital O is carbon monoxide. Capital C, little o is cobalt. Our last type of compound in this ionic nomenclature is something known as the hydrate. Hydrate's an ionic compound with water that's incorporated into the crystal lattice, and the amount of water is specific to the compound, therefore it can be included in the formula. So to name these, you name the ionic part of the compound according to the proper system that we have just covered, and then you add the word hydrate that's then preceded by a Greek prefix indicating the number of water molecules. As an example, at BaCl2.2H2O. BaCl2.2H2O. The dot means electrically attracted to. It does not mean multiplication. So this is going to be, the ionic portion is here. This is barium chloride. No Roman numeral is needed here because barium is in group 2. We then have hydrate, preceded by a prefix that means 2, which is di. So we have barium chloride dihydrate, barium chloride with 2 waters. MgSO4.7H2O. MgSO4 is magnesium. SO4 is sulfate. Magnesium gets no Roman numeral. Like barium, it's part of group 2. And then we have hydrate. Prefix for 7, heptahydrate. Magnesium sulfate heptahydrate. Going in the opposite direction, cobalt 2 chloride. Cobalt positive 2, chloride negative 1. This is the ionic part. Use oxidation numbers here, 2 and 1. That gives COCl2 dot 2H2O, 2 water, dihydrate. Copper 2 sulfate pentahydrate. Copper 2, copper with positive 2. Sulfate is SO4 with a negative 2. Positive 2, negative 2. This is a 1-to-1 ratio. CuSO4 dot. Penta means 5. Hydrate means water. Sodium acetate trihydrate. Sodium is Na+, acetate is C2H3O2 minus. Positive 1 and negative 1. So this is NaC2H3O2 dot. Tri is 3. Hydrate is water. And then we have sodium carbonate, sodium positive 1, carbonate, negative 2, whole thing is negative 2, or 1 out here, or 2 over here, so the final finished product is going to be CO3, no parentheses around carbonate because there's only one of them, dot, deca means 10, hydrate means water. So the prefix gives a coefficient this time instead of a subscript. That completes this podcast. Make sure that you have clean notes and that you've uploaded them to get credit for watching this video.